Okay, so before I will start this third lecture, I'll try to very quickly tell you about the structure of the lectures which remain. So, as Jeff explained yesterday, we'll see three completely different approaches which lead to noise sensitivity. One is hypercontractivity. Another one will be called randomized algorithm. And the last one will be a geometric study of frequencies in the plane. So the nice advantage here is that these three approaches will be completely independent of each other. So, and the rest of the lectures will be structured as follows. In this lecture, the third one, we will use this technique to prove the KKL theorems as well as the Benjamini-Kalaitram theorem on noise sensitivity. So this will be the content of this whole lecture. In the fourth lecture, we'll see two directions. The first one will be, so the fourth lecture. The first one will be to use the Benjamini-Kalaitram theorem to get the first result about noise sensitivity of percolation. Sensitivity of percolation. And here we'll discuss a little bit what should be the right level of noise sensitivity of percolation, and this will be the purpose of the other techniques later on. And the second part of the fourth lecture will be to apply the techniques that I will introduce here to the case of anomalous fluctuations. For this random metric that I introduced in this PDF file at the beginning. So somehow the third and fourth lecture will be about these hypercontractivity techniques, but later on we won't rely on this anymore. So the talk today will be very analytical, but later on we'll have completely different techniques. This will be the content of the fifth lecture, and this will be the content roughly of the sixth and seventh lecture. Now it starts being a bit less predictable, but roughly. And in the very last lecture, so the eighth lecture, we will use both of these techniques, but not this one, which won't be powerful enough. Both of these techniques to have results about dynamical percolation. So in the last lecture, based on the knowledge on the noise sensitivity of percolation that we will get here, we'll prove that there are exceptional times of percolation and things like that. Okay, so this is just to give you a rough idea of what will follow now. So today, so the chapter today will be proof of KKL and BKS via hypercontractivity. So the first goal is to prove, or I'll rigorously prove only this one. The second one is very similar. So the goal is to show you how to prove such a general statement. So when you read the proof the first time, you find it a little bit mysterious. It goes into the Fourier analysis and things like that. So to start with, I will try to remove some of the mystery of the proof by explaining to you the strategy that is behind and on a heuristical level. And this will enable me to explain to you how hypercontractivity comes into the picture And only then we'll start rigorously the proof of the theorem on the left. So I wrote these theorems just to recall you their statements. I already gave these statements to you in the first lecture. So the first one says that whatever function on the hypercube that you're looking at, you will always find one of the variables which will be rather influential in this sense. The second statement tells you that there is the following rather subtle balance. If you take any Boolean function, if you want to make its total influence, meaning this, which is important in the sharp thresholds and things like that, if you want to make it very small, well, it's not such a good idea to make all the individual influences very small as well, right? Because if you do, then it actually gives a push on the sharp threshold here. So this theorem is about this nice balance. And on a heuristical level, I'd like to explain where this comes from. So, okay, so now, for some time, it will be only heuristics. So, recall that Poincaré's inequality what it says is the following. If you take any Boolean function f, its variance is bounded from above by the total influence, which is the sum of all the influences. Okay, so now what does this theorem here says? It says the following. If one assumes that influences are small, then in fact you can improve on the Poincaré inequality as follows. The variance of your Boolean function will be much smaller than the total influence. So of course much smaller depends on how small the influences are, but in these heuristics I won't give anything quantitative. So now I'd like to explain what is the strategy to see this improvement on the Poincaré's inequality. So the strategy will be of the proof will be a spectral analysis of influences. Or in other words, the strategy will be to understand in terms of the Fourier spectrum what it means to have small influences. So this assumption, it implies something on the frequencies which will help us understanding that. Okay, so to go through this strategy, let me recall very quickly what Jeff said yesterday. So if you take a function from the hypercube into 0, 1, or even into the real numbers, you can decompose it as a Fourier expansion like that. And we call that the Fourier coefficient was the expected value of f times this function chi of s, which is just the product of all the bits that are in the set S. And the influence is intimately related to this Fourier expansion as follows. So you can introduce the discrete derivative at the case variable. So you look at what is the effect of the case variable by introducing this function, delta k of f of omega equals f of omega minus f of sigma k of omega. And this will be very important through the whole lectures. Remind that this is always, this takes its value into -1, 0, or 1. So this is not exactly Boolean, but this is there is a big discrete constraint on this discrete derivative. And the L1 norm of this discrete derivative are exactly the influences. Okay, why is that? Because if you take the integral of this, when it's 0, it means the case variable doesn't have any effect, and else it's exactly what you want to measure. And now, and it will be important later, since the function has values into -1, 0, 1, the L1 norm is the same as the L2 norm squared. Okay, so now how is the notion of influence related to the spectrum of the function f? This works as follows. So write f of omega to be sum over s of this times that. Now look at, flip the case variable. So do the same expansion, so you end up with this. So now, by subtracting, you get that the discrete derivative of omega equals the sum over s of this times the difference of these two. And as Jeff explained, if the case variable doesn't belong to the set S, it gives you 0, and else it gives you twice, it gives you 2. 2 times the chi of S of omega. So this is the computation that Jeff did yesterday. So when you do the difference, you only keep the frequencies that in which k, for which k is in the frequency, and you get twice the Fourier coefficient of S times chi f of omega. So this thing, as Jeff explained, exactly gives you the Fourier expansion of each of the discrete derivatives. Okay, so it tells you that for any S, the Fourier coefficient of delta k of f is either twice the corresponding Fourier coefficient of S if k is in S, and 0 else. Okay, so here I just recalled what was done yesterday, but now in these heuristics, I should use this hypothesis that we are assuming influences are small. So what does it mean? So influences are small. It means, so IKF small. It means that it's exactly the same. This L1 norm is small. But now this function is like, it's almost like an indicator function, right? It has values into delta k of f has values into -1, 0, 1. So now you probably know from Fourier analysis that if you have the indicator function on an event which is very small, by the so-called Weil-Heisenberg uncertainty, having small support, it implies that the Fourier transform of this function should be very spread among all the frequencies. Should be spread. So of course this is only heuristical here, so I'll have to make it rigorous later, but somehow that's very believable. And it's even more, since most of the frequencies are of high cardinality, what we'll get is that the Fourier transform of delta k of f is mostly supported on high frequencies. So if you just want an analog of this vague statement, so an analog would be as follows. If you take a periodic function on the interval, which is an indicator function with a small support, then it's an easy exercise to show that indeed most of the spectral mass of this function is supported on high frequencies. On the high frequencies. And somehow you can see on this picture that if you wanted to write it as a sum of cosine and sine, well, you won't have so much contribution of first frequencies here. So in our Boolean setting here, the cosine of small frequencies, they correspond to this chi of s, where the s have very small cardinality. So later on, we'll have to make this part rigorous, and this will be the main content of the proof. But now let's see how one can conclude from such a uncertainty principle. So if we assume that these influences are small, and if you buy this fact that indeed the Fourier transform is concentrated on high frequencies, what does it mean? It means that we can find some large m, so that for all the variables, the sum over the frequencies which are of cardinality smaller than this large m of delta k of a squared is much smaller by this Weil-Linsenberg uncertainty than the complete sum. So this is exactly stating that if you look at the Fourier expansion of these functions which have small support, most of their frequencies, they're higher than the level m somehow. Okay, so now let us try to use this statement. So maybe so that I don't go very quickly, you see here that the Fourier coefficient of the empty set, which is just the average of your function, this is 0. Okay? You can see it from here. Basically, this is because the average of this is the average of this minus the average of this, so you get 0. So by Parseval, here you have the sum of all the Fourier coefficients squared. So, and 0 is not missing. So by Parseval, this is just the L2 norm squared of this. And this, recall that it was exactly the influence. Okay? And now, let us use the knowledge we have on the Fourier coefficients of the discrete derivative here, because we know that the Fourier transform of this discrete derivative is intimately related to the Fourier transform of the function f itself. So this translates into sum over these frequencies, but only the frequencies where which include k matter, and you get that 4 times these frequencies is much smaller than the case influence. Is this okay at this point? So now I erased it, but in KKL, you want to compare the total influence with the variance of your function. So now let us sum over all the variables k. And let's see where this leads us. So if you sum over k, on the right, you get the sum of influence, or in other words, the total influence, I of f. And on the left, what do you have? If you sum over all the case variable, each frequency s will appear cardinality of s times, right? Because it has cardinality of s different variables in it. So what you get is that 4 times the sum of the frequencies like that, of s times this, is much smaller than that. So in particular, it gives that, because remember that, okay, maybe before that, remember that what we want to prove is that the variance of f is much smaller than the total influence. This is the goal. And what is the variance of f in terms of the Fourier coefficient? Well, variance of f is the expectation of f squared minus the average of f squared. And by Parseval, this is the L2 norm squared of f. So this is the sum of all the Fourier coefficients. And this one is the coefficient of the empty set squared. So what you get, and maybe Jeff proved it yesterday, I don't remember, is that the variance is just the sum over all the non-empty Fourier coefficients of f of that s squared. So now we're almost there, but not quite yet. So let us force the appearance of the variance. This is easily seen to be bigger than sum over all the frequencies of this. So we lose a lot here, but it will be okay. So we get that we don't yet get that the total influence is indeed much larger than the variance, but we get that at least the total influence is much larger than the contribution to the variance given by the first m Fourier coefficients. So now we're almost done in these heuristics. How do we conclude? Let us look at the energy spectrum of the function f. So the energy spectrum was to look for each value of m, how many frequencies of cardinality m contribute to the variance. So here we may look at the function of m. Okay, maybe I should do it bigger. Should look at the sum over the frequencies of size m of the contribution of the spectral mass here. So this was the energy spectrum EF of m. So if you plug this energy spectrum as a function of m going from 1 to all the way to the n variable, you'll have some shape. So, for example, a spectrum like that. And if you sum the contribution of all these values of the energy spectrum by this formula which is here, you get the variance of your function. Right? So the integral of this shape here is exactly the variance of your function. So now m, this value here, we know that this is large by this uncertainty principle which pushed all frequencies toward high frequencies. So m is, I don't know, somewhere here. So now we have two cases. Imagine that, say, half of this spectral mass is below m. If it is the case, it means that here you get at least half of the variance. And here you're done, because indeed your total influence is much larger than the variance of your function, and you improve on the Poincaré's inequality. So now we have to do the second case. Imagine that our Boolean function f is of high frequencies in the sense that most of its energy spectrum, maybe not all, but a big portion of it is above n. So here we can't conclude right away, right? Because this would not be true anymore. But we are almost done anyway, because what does it mean? It means that, so at least say half of the spectral mass is above m, so it means that the sum of the frequencies above m is larger than 1/2 times the variance of f. And now recall something that Jeff explained yesterday, but this follows from computations we've already done today. Recall that the total influence is 4 times the sum over all the frequencies of s times this. This followed from this interpretation of the influences in terms of the spectrum. And we had such a formula here, but we stopped at the level n. So using this formula, you're done because this is obviously bigger than the sum of the frequencies larger than m of this times the value m, because for others it's even bigger. But now we assume that a positive fraction of the spectral mass lies here. So we get that this is bigger than m times the variance of f. And since this threshold m, this cutoff m was large, we get that indeed the total influence is much larger than the variance. Okay, so now I'm done with the heuristics. It took much longer than I thought, but so now the whole idea is to try to exploit this Weil-Heisenberg uncertainty, which pushes the frequencies toward the high spectrum, toward high frequencies. So there are several parts that need to be made quantitative in this program. So for example, how large should M be taken, but this will be okay. The main part is to try to make sense of this here, right? To try to have a quantitative way to say that indeed if influences are small, I can say that frequencies are pushed toward high frequencies in such a way. And that's hypercontractivity, which will enable to do that. So now, what I'll do is that I'll explain to you quickly what hypercontractivity is about. So, small digression on hypercontractivity. So the context where it appears is the following. Take Rn and dot with the Gaussian measure, and consider the ith kernel k of t. So you all know that if you take some function f on Rn, and if you look at the operator which associates to it kt of f, so basically you apply the ith kernel to the function f, you know that it regularizes the function f, right? So, well, you know that if you have some rough function and you noise it a little bit with the Brown motion, you'll get something much nicer. So there are several ways to think of this regularization. For example, a functional way would be as follows. If you think of L infinity over n, and if you apply to it the ith kernel for a time t, you enter into smooth functions. So this is a way to think of this regularization. Hypercontractivity is another way to think of it. So if you take some q in 1, 2, and you take some function f in LQ of Rn, but let's say not in L2. So for example, think of a function that blows up so that it's not in L2. If you apply to it the ith kernel, kt of f, it's not very hard to see that this will be in L2. So if you apply the ith kernel, if this goes to infinity, somehow you may be very high, but you'll regularize the function f. So somehow if you look at the operator kt, it maps linearly LQ into L2. Well, linearly might need some more work, but that's the case. And you might wonder about what is the norm of this operator from LQ into L2. And somehow hypercontractivity gives you information on this norm. So I won't state it exactly as a way to get an information on this norm, but rather as follows. If you take any function f from LQ, which might not be in L2, if you wait long enough, when I say wait, I mean under the ith kernel, if you wait long enough, t bigger than some parameter which depends only on the starting regularity q. So when q gets smaller, gets closer and closer to 1, you can have nastier and nastier singularity here. So if you wait long enough, we already know that kt of f is in L2. But what happens here is actually that the L2 norm is less than the LQ norm. So in other words, if you wait long enough, the norm of this operator here, kt, from LQ to L2 is less than 1. Your operator is a contraction. And this holds for t bigger than tq. So this estimate is, of course, important if you are in that kind of field, and it was very important in the 70s in rigorous constructions of Euclidean field series and things like that. And somehow also Nelson introduced these things, and I don't know what proof Nelson did, but Gross proved this thing by actually first proving it on the hypercube, and then sort of used the central limit theorem to deduce the Gaussian case here. In some sense, the hypercube was done first, and this is what will concern us here. So let's move back to the case of the to the hypercube. So before I state what hypercontractivity is there, I first need to have an analog of this regularization operator here. So what we will take as a regularization operator is the following one. Take the operator which to a function f associates the expectation. So now I can use notation that we used in this course so far. So you take some Boolean function f, or even some function f defined on the hypercube with valued into the real number. So and you noise a little bit your configuration omega, and you look at this operator. So this is exactly the same thing as in the case of the heat kernel, where you sample an omega according to the Gaussian measure, and you noise it according to a small Gaussian of variance t, and you look at the conditional expectation. So if you look at what it gives in terms of frequencies, if this has the following expansion, once you apply the operator, you can easily compute that this will give this. So therefore, let me introduce the following notation. For any rho in 0, 1, let us look at the operator T rho, which to f equals sum of this times chi of s, associates the function So in what follows, you may think of this parameter rho as 1 minus the noise. So for example, if you start with a Boolean function here, this conditional expectation here, of course, is not necessarily a Boolean function. It's going to be real valued. So exactly as in the continuous case, this thing is a regularization operator, and it satisfies the same kind of hypercontractivity. And the statement is as follows. So it's known under the Bonami, Beckner, and I guess we could add Gross, who first proved it for the, and then extended to the Gaussian case. And this says that for any function from the hypercube into the real numbers, the L2 norm of the regularization of f with a noise 1 minus rho is less than the LQ norm of f. But here I didn't make the dependence in where is it? In Q explicit. here we'll need to know quantitatively how explicit it is. And if we regularize by an amount rho, we will send L 1 plus rho squared into L2. So this is what hypercontractivity tells us. So now you might think, well, okay, LP, LQ all over the place. Well, how come this would give anything like the Weyl-Rosenberg uncertainty for us? So let us see why it indeed gives what we want. So remind that we had this delta k of f, and we assumed that they had small influence, right? So they were in minus 0, 1, and we assumed that this was small. Or it's the same as assuming that the L2 norm squared is small. So let us see what hypercontractivity tells us applied to this function here. So let us apply it. So let us apply this noise to the discrete derivative at the variable k. And Bonamy-Beckner tells us that the L2 norm of it is smaller than the LQ norm with q equals 1 plus rho squared. So if we square it, this gives us this. And now remember that this value, this takes value 0, 1, or minus 1. So it makes it very convenient to compute its LP norms. They have nice relationship between each other. And it's easy to see that this is the same as the L2 norm of your function, but you need to change the factor on the top. And if I'm not mistaken, you get this. So now, remember that rho was into 0, 1. So 1 plus rho squared is smaller than 2. In particular, this power here is strictly larger than 2. And we assumed that this function has a small support. So it implies that this quantity here has to be much smaller than this L2 norm squared. And now we start being in good shape. Let us write down what this inequality means. So if we write it on the Fourier side, using Parseval both directions, it gives us that the sum over the frequencies of rho 2 to the s delta k f of s squared. So why that? It's because the L2 norm squared of this is what I wrote here. We're saying that this is much smaller than the sum over s of this. And remember that the average is 0, so we get that. So now if you think just a little bit, this exactly tells us what we want, namely that it's impossible that half of the spectral mass of this function is supported on low frequencies. Because if you take rho equals, I don't know, 1/2, this term is not so small for the first part of the spectrum, but this is much smaller, so the frequencies has to be pushed toward high frequencies. So this inequality, which comes from this sort of functional analysis, exactly encodes the phenomenon that we need. So now end of heuristics and digressions and things like that. Let's prove KKL. Yeah?
Why the fact that the other one is smaller means that you are concentrated on small set?
Yeah, that's a good question. So what we use here, so if you have a function whose L1 norm is small, it doesn't necessarily mean that you have a small support or anything. But if you know that your values into this, then it has to be of small support. Okay? So we really use at different places the fact that our function is Boolean, that it has only two values possible. We use it with this intuition of small support, and we use it a lot, for example, here when we play with different LP norms and things like that. So this is completely crucial. So okay, so now let us go into KKL. I will only prove KKL1. KKL2 is in the notes. Somehow KKL2 is slightly stronger than KKL1, and this will be done in the exercise stations. But let us do KKL1. So here we start with a Boolean function. And what's nice in this theorem is that we don't assume anything. And now we want to prove this statement. So we want to localize to find some variable which has influence larger than this log n over n times the variance. So we can assume that all variables for any k, the influences are smaller than this quantity. So I'm not trying to do a proof by an absolute proof, because this is still way above the log n over n that we're looking for. But we may assume this. Why? Because if it's not the case, you have one variable which is larger than that, and since it's much larger than log n over n, you're done. So let us assume this. And why do we start with such an assumption? We will use these heuristics that it pushes frequencies high, and we want to be reasonably comfortable. So we assume that somehow this is very small. Somehow these delta k of f have a very small support. And now let us proceed to a computation. So it's too bad I erased it, but somehow at some point we had two cases in the heuristics. When we looked at the energy spectrum of F, there was some large values, and either a positive fraction of the spectral mass was here, either it was only toward high frequencies. So in this proof, with this assumption, actually we are in the second case. So let us try to prove that most of the frequencies are very high. So choose, well, let M some large number whose values will be fixed later. So here, it's not the heuristics as before, right? In principle, I will really choose carefully things. And let us try to show that the first part of the energy spectrum is small, that most of the Fourier coefficients are on high frequencies, and this will be enough for us to conclude as we did in the heuristics. So this is less than 4 times the sum of the frequencies of this. So now we know from the heuristics that we'd like this to be much smaller than the sum of the influences. And this step was using the Weil-Heisenberg uncertainty. And I claim that in order to use it, we want to use this hypercontractivity. So let us make the regularization appear in this formula, sort of in a brute force way. So this is less than sum over S, 2 to the 2 to the m, and 1 over 2. Oh, sorry, here it was for cardinality between 0 and m, and this is cardinality between 0 and m. And then we have this. Okay? So this is less. I will just add the frequencies above m with this regularization term here. This is less than 4, 2 to the m, sum of s, 2 to the s, like this. And now with the same manipulation as we had before, when we see this, you recall that this is like summing over all the variable k and looking at the discrete derivatives. So this is exactly the same as this, sum over the variables of, by Parseval, the L2 norm squared of this. So here we apply the noise, which is of order epsilon, and this corresponds to this. So now we've not done anything, we've not used anything conceptual. Here we use Bonamy-Beckner, or if we prefer, we use hypercontractivity. And this tells us that this is less than this times the LQ norm of this function, where Q is 1 plus rho squared, and rho here is equal to 1/2, because we had this factor here. So we get an LQ norm of 5/4. So if I rewrite this, you get that the contribution of the first frequencies on the left is less than 2 to the m times the sum over the variables. Here, let us use the same thing as before, that there is a relationship between the LP norm. So this is like 4 over Q. And Q is 5/4, so this gives 2 to the m sum over k. And 2 over Q is equal to, 8/5. And we call that this is the influence. So we get less than this sum over the variables of the influence to the power 8/5. Maybe I should have warned you that there would be some computations, but it's soon. It's almost done. What? Yeah, this is equality. This is equality. Yeah, and where? And this is also equality. So now let us use the assumption that I did at the beginning, that influences are small. So this is less than this times n to minus 3/4 times that. So this gives 6/5. And times the variance of f to the power 8/5. But f, remind that this is a Boolean function, so this has values into 0, 1. So the variance is smaller than 1. So the variance to this big power is smaller than the variance. So we get this. And now we have, so that's not an equality here. And since we have n variable, we'll have n times n to the minus 6 5s. So this gives this. Variance of f. So now we are done because we still have to choose this parameter, but this goes so quickly to 0 that we have a lot of free room for that. So for example, take m equals, I don't know, this, log 2 of n, so fairly large. This gives you that sum of the frequencies below this cutoff is less than basically n to the minus 110, this would be fine, times the variance of f. So in this picture, it means that really most of the spectral mass, just up to this very small n to the minus 10, most of the spectral mass is above a logarithmic factor. In particular, so the influence of f, which is sum over all the influence, which is by this formula the sum that we used maybe 5 times already. This is bigger than this value m here. So 1 over 100 log over 2 of n times the contribution of the Fourier coefficient, which are above this cutoff. And we said that this was more than 1 minus n to the minus 110 times the variance of f. So now, well, this is basically 1, right? So we prove that when influences are so small as what I assumed before, the total influence is larger than a constant times log n times the variance of f. And now, since this is the sum of all the influences, at least one of them has to be bigger than what we wanted, i.e. log n over n times the variance of f. And we are done because since if this was not satisfied, you would be done anyway. So somehow, well, this was a bit technical, but I find it quite surprising that eventually, here you lose a lot of things at many different steps. It seems you're not paying really attention, you're not very careful at optimizing the proof, but eventually you get a result which is completely sharp. So, okay. So, now I'd like to say a few words about the generalization of it. Namely, yesterday when Jeff proved that these theorems about sharp threshold, it relied a lot on the fact that the KKL theorem holds for all values of P. Right, when you take percolation, knowing that there is a big derivative at PC is not enough to tell you that you have a sharp threshold. So somehow you need to have such information on influences for all values of P. The theorem was roughly as follows, that for any f, there is always a variable so that the P is influential, the case influential at level P is bigger than some constant, which is universal and which does not depend on the parameter P, times the variance for the P measure, so where here the P of n is p delta 1 plus 1 minus p delta minus 1 to the power n. So this was bigger than this times the same log n over n. So if you want to prove this general statement, the proof that I use here is completely restricted to the uniform case. The Fourier analysis only works in the, I mean, these chi-s functions are orthogonal only for the uniform measure. A first idea would be to proceed into different steps. The first one would be to find orthonormal bases for the p-biased measures. So extend the Fourier analysis to this measure. And then to try to prove an hypercontractivity estimate, LQ going into L2, for these p-biased measures. And if you manage to do both, and that's doable, you hope to get the same thing with the same proof. But somehow it seems that it doesn't work out very nicely in the sense that this constant that you would end up with would not be uniform over all the parameter p's. Near the edges, you would have some troubles. So we won't do that, but there is a very nice way to extend the KKL theorem to all the measures, all the p-biased measures. And this follows from the following result. So KKL was long, but now this is even longer. This is called BKKKL. Yeah, so of course some of these K are the same as previously. This is Bourgain, Kahn, Kalai, Katz-Nelson, and Linai. And they extended the KKL theorem as follows. They say that there is a universal constant C such that if you take any function, but this time we leave the discrete case, we define it on the continuous hypercube, so it can have any, the input is much larger, but, and that's very important, we keep this constraint that we have only two values. So somehow this hints that in the proof we used, the input we had some Fourier analysis here, but this is really the constraint and the target that gives these nice phenomenons of log n appearing and things like that. So if you take any function on this, there is always one variable such that its influence is larger than C times the variance of F times the same log n over n. Where here you define the influence of the case variable as the probability that when you change the case variable, you may do a switch on your function. So if one assumes that we had this theorem available, then it's not very hard to recover this one here, because basically when you take a function f and you look at a p-biased measure, you produce a function by projecting in the right way on this hypercube here, and you conclude what you want, and you use the fact that this thing is completely uniform. So I won't do it, but I think maybe in the exercise sessions it will be done somehow. I'll explain just in 2 minutes how one can prove such an extension. So originally they went through the whole Fourier analysis and they've done the stuff again. But Friedgott noticed that there is a nice way to recover somehow this theorem from the KKL that I proved. Yeah. Sorry? The influence is okay. Take, for example, the n equals 2 and say that I have this function. It's 1 here, 0 here. Okay? The influence of this variable here would be the probability that no, sorry, let's look at the influence of the second variable. The influence of the second variable is the probability that it makes a difference. So the probability will be exactly this interval, because if the first variable is anywhere here, the second variable can make a difference on the output. Well, if the first one is here, you can't make any difference. Okay? So it's just the analog of the discrete case. You look at the probability that your variable is pivotal for the outcome. Okay? So how to recover PKKL from the uniform case? So say this is our hypercube, continuous hypercube. Ah, no, sorry, there is a, well, there is a first step, which is a little bit like in when you want to prove isoperimetric inequalities or things like that. Often you may have symmetrization procedures which simplifies your problem, and here it's similar. You have a monotonization procedure, which when you have any function like this, into this, you may produce by a monotonization argument a function out of f, still from this hypercube into this, such that for any k, the influence of the case variable of this function is smaller than the original one. So it's exactly like in isoperimetry where you symmetrize this and you have a monotonicity like that. So in particular, it's enough to prove the BK-KKL theorem for monotone functions. So now let us take some G monotone on this. And let's say this is the continuous hypercube. So now this result looks at the uniform measure on this hypercube, and you have some function G which is monotone. So the graph has to be monotone, means that if you go like this or like this, you can only increase. So you have some graph of your function here, and you have the uniform measure in this. The idea is simple but nice. So you want to approximate the uniform measure by the discrete measure here of mesh 2 to the minus m. And what you do is, instead of looking at so you will approximate your function g by a function like that, where instead of taking the uniform measure, you'll take this discrete measure, but this one you can recover from a uniform hypercube. And so this would be defined on 0, 1 to the n, and this would be defined on an hypercube, but this time I need a larger dimension. So why that? It's because a uniform variable, u, you may approximate it by the sum from k equals 1 to n of delta k times 2 to the minus k. And delta k being Bernoulli variable into 0, 1. Okay, so, well, this is a bit rough, but somehow this function defined on your continuous hypercube, you may approximate it by a Boolean function, which would be defined on a much larger hypercube, endowed with the uniform measure. And now you can use the KKL1 and KKL2 theorems, and this provides you, this gives you the BKKL. There is one step which is a little bit messy, which is that you need to handle the approximation that arises at these places here. Okay, so this was just to tell you how to extend KKLs to other measures, and therefore to have all these sharp threshold theorems and so on. So now in the remaining of the talk, of the lecture, I'll prove the Benjamini-Kalai and Schramm theorem. So let me state again the theorem. So if you take a sequence of functions from this hypercube into 0, 1, and if you assume that this functional, which we call the h, which is the sum from 1 to m of n of all the variables of the squared of the influences. So this is the L2 norm squared of the influence vector. If you assume that this quantity goes to 0 as n goes to infinity, then it gives you that necessarily your sequence of function is noise sensitive. So last time I said if and only if. That was wrong. So if you get that, you know that your function is noise sensitive, but obviously this doesn't go the other way around. For example, the parity function that I introduced in the first lecture is maybe the most noise sensitive function, but all the influences are equal to 1, so you're far from this criteria. So if I have time at the end, this would be an if and only if in the case of monotone Boolean functions. So this result in the first part of this course is very nice. Unfortunately, I'll prove it in a slightly weaker case. So in this theorem, the result is completely independent of the speed of convergence of this quantity. So no matter how slow it goes to 0, you know that your function is noise sensitive. Today, we'll assume that there is some exponent such that it could be very small, but some exponent so that this functional is somehow polynomially small. So to apply the same ideas as in the KKL theorem, we need to know that this goes to 0 quickly enough somehow. But for the purpose of these lectures, this is not too bad, because when we will apply this theorem to percolation, this will actually turn out to be the case. So at least this will be self-contained. So if we assume this, now we want to prove that. In fact, we can prove something slightly more quantitative about this noise sensitivity under this hypothesis. So maybe this is BKS prime. Under this hypothesis, there is some number which depends on how bad the exponent is, so that the sum of all the frequencies of size less than m times log m of n, this will go to 0. So this is quantitative because it tells you that if this functional goes to 0 polynomially fast, in some sense, we'll see later in the course that this gives a logarithmic noise sensitivity for your sequence of functions. So under this, let us prove this theorem. So I'll proceed exactly as in the KKL theorem. So again, there will be some lines of computations, but I hope it will be fine. So we want to prove that this is small. So to avoid one line, let me do this. This will be smaller than 4 times the sum over S times m log m of n of this times that, which is smaller than 4 times. So I do the same trick as before. I want hypercontractivity to come into the picture. So 2 times m log m of n times sum. Oh, no, sorry. So in KKL, we didn't need to be very careful about the regularization that we used in the hypercontractivity statement. Here, we need to be slightly more subtle. We'll choose the regularization term later. So, and this is a minus. And we get this 2 to the S, S, and this. Okay, so you recognize here that this is, as in the case of the KKL proof, this is an equality, as Ron might point out if I do the mistake. It's exactly the sum over all the variables of the L2 norm squared of the regularization of the case discrete derivative. So now we apply Bonami-Beckner. And this gives us that this is less rho, the same thing, times sum over all the variable delta K of F, Q squared. So we call that Q equals 1 plus rho squared. And this is exactly, and again, this is because this is into minus 1, 0, 1. So the LP and the LQ norms, they have nice relationship. This is exactly the same as the sum over K of delta K of F, 2, 4 over Q. And this term is equal to the influence of F to the power 2 divided by Q. So now we have a term which is almost the criterion in the BKF theorem, except instead of the to the power 2, we get to the power 2 over Q. So that's what we end up with. So let us use Hölder inequality. So, okay, so let me write it down so that I don't mess things up. Well, supposedly I should know it by heart, but at least for you it might be helpful. For me it would certainly be helpful to follow the computation. So now applying this with P equals Q to make the BKS criterion appear. What we started with at the beginning is less than rho to the minus 2m log m of n times the sum of the influences squared and to the power 1 over p. So I said p equals Q equal of. Okay, that's really bad because this Q has nothing to do with the. Okay, so this Q is 1 plus rho squared. And I want P to be 1 plus rho squared. So 1 over P would be this. So 1 over Q, but this time the usual Q in Hölder. This will be rho squared 1 plus rho squared. So now if I apply Hölder here, I get 1 over P here. So I get 1 plus rho squared. And then I get B would be equal to 1, and I have m of n variable. And to the power 1 over Q, this gives rho squared 1 plus rho squared. So now let's use the assumption that we had that this goes polynomially fast to 0. This gives less than rho minus 2m log m of n times m of n to the power, so to the power what? Well, there is this rho squared here to the 1 plus rho squared. And here, this is less than m of n to the minus delta. So here, we get minus delta. Okay, so now remember that delta is fixed. So, but we can still play with the regularization term rho. So now choose rho small enough so that rho squared is smaller than delta. This goes polynomially fast to 0. So now you just need to choose the m depending on your delta, basically, so that this doesn't overshoot this term here. Okay? So since there were already many balls of calculation, I mean, that's very easy, so you can do it. And you get that, indeed, all the frequencies which are below this logarithmic term go to 0. So now if you recall Jeff's lecture of yesterday, this means that the energy spectrum spread to infinity pretty quickly. So this means that the energy spectrum of f of n, which by definition is the sum of the frequencies of size m, of the contribution of these Fourier coefficients, if this is the cutoff m times log m of n, the spectral mass asymptotically is pushed at least at this speed. And if you recall this formula about the covariance of f of n of omega with f of n of omega epsilon, which was the sum over the non-empty frequencies of fn of s squared and 1 minus epsilon to the power s. Then, as Jeff explained yesterday, if you know that the spectral mass goes spread to infinity, asymptotically there is nothing remaining on the finite frequencies, and since this on high frequencies gets smaller and smaller, you get that indeed this is noise sensitive. So there was a proposition yesterday that was telling that indeed if you can prove such an estimate, then you're done. You know that this is noise sensitive. So somehow all the KKL technology here carries through and gives this nice criterion that to prove that a function is noise sensitive, you may just prove that this is the case. So in the paper by Benjamin Kalai and Schramm, things are more complicated because in fact, this is true, as I said, independently of the speed of convergence. And somehow, following exactly the approach of KKL doesn't really work out. You need to use sort of deep estimates from papers of Talleyrand. And they had to generalize these estimates by Talleyrand, so I won't go into this. But there is a remark in the notes and which points to a paper, and if you're curious, you can go into that. In the last 5 minutes, I'd like to yeah.
If you use the fact that the exponent is 2, would this be true with exponent 3 or 4?
Okay, so if you have less than 2, for example, then it cannot be true, because if you take the majority function, somehow this criterion is exactly critical. So if you take 2 minus epsilon,
Why do you use the fact that it's 2?
What do I use? That's a good question. Okay, so let's assume for a second that 2 was equal to 3. So in that case, this would go to 0 even for the majority function, but hopefully the proof should collapse, because this is not noise sensitive. And That's a good question. I would have to think about it. Hopefully it collapses. Okay, so in the last 4 minutes, I'd like to show you a small remark, but I think this is an interesting phenomenon. So to see what this says in the case of monotone functions. So before saying this, here's the following remark. If you take f to be a monotone function, monotone, then we've seen that influences, they have a nice interpretation in terms of frequencies, and we used it a lot today. In the case of monotone, this interpretation still holds, of course, but there is another interpretation completely different, also in terms of the Fourier spectrum, which is very useful, and this is as follows. So take any k, any variable k, and look at the Fourier coefficient of the singleton k. So, you know, you have this Fourier coefficient of subset S. The subset S could just be one variable, right? So what is it? This is the expectation of f times this chi of S, where S is this singleton. And now, what, after all, is this chi of S? Chi of S, you might have forgot. I hope not, but you might. Chi of S was the product over all the bits in S. So here, this is f of x1, xn. And this chi of, x, no. Okay. This function chi of S for S equals k, this is just the k's bits, which is a plus minus 1 bit. And now, computing this is easy. So one way to look at it is to say that this is the probability that k is pivotal times this expectation xk, knowing that k is pivotal, plus the probability that this is not pivotal times this conditional expectation. But if you think of it, if k was not pivotal, it means the k's variable doesn't have any influence. It's a plus and minus 1 bit, so when you average it, it just gives you 0. So only this term remains. This, by definition, is the influence. What is this? If you know that k is pivotal, well, with probability 1/2, this is equal to 1. We know that this makes a change in the function. The function is monotone. So if this makes a change and this is 1, f has to be 1. And when this is minus 1, this has to be 0. So you get that the average of this is 1/2 times 1. So this gives you 1/2. And here we use monotonicity. So somehow the conclusion of that is for any variable k, the influence at this very simple expression in terms of this Fourier coefficient. So this is a very different interpretation as the one using this delta k of f. So now you see that sum of the ek of f squared goes to 0. This is equivalent to the sum of the Fourier coefficient of size 1, k in n, is going to 0. So in other words, if I take some monotone function, and if I start drawing for you its energy spectrum, so again this, if I just start telling you, okay, this has a very small first layer, if here the energy spectrum is small, meaning that the sum of the contribution of all the singleton is small, which is the first layer. I write these things 10 times, but this is so that it really enters. So if I tell you that this is small, then I know that the BKS criterion is very small. And therefore, without drawing to you the rest of the information, the spectrum has to be small at the beginning. So when you have a monotone function, it reveals to you a big restriction on the possible shapes of the energy spectrum. Having a small first layer, whatever you do, it pushes your frequencies very high if you're monotone. So that's, I think, an interesting phenomenon. And what's very easy to see is that we prove this direction for monotone function. But of course, the other direction is completely trivial here. If you have a sequence of monotone function which is noise sensitive, well, as Jeff explained yesterday, all these layers have to go to 0. In particular, the first one has to go to 0. And we've just seen that the first one is up to constant the same as the BKS criterion. So that's equivalent. Okay, so unless there are questions, I'll stop here.